Welcome to the sixth set of presentations in the second webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a scientific solution, engineering solution, and a solution to human welfare challenges through the promotion of adsorption research and education. We hope that all of our attendees and their families and their colleagues are safe amid the ongoing COVID-19 pandemic. We thank everyone for attending the webinar today. The webinar series, which began in the spring of 2020 and then restarted last autumn, has been an immense success, and the recordings of those webinars continue to be viewed on YouTube. We continue to plan these webinars through the present academic year with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Subsequent webinars will be announced on the IAS mailing list and the IAS Twitter feed. Today's webinar will be given by Danny Shade, a PhD student at the Georgia Institute of Technology, and Kasturi Nagesh Pai, a PhD student at the University of Alberta. Both of these students were Best Poster Award recipients at the inaugural IAS Twitter Poster Conference. I am Nicholas Wilkins at the University of Alberta and the IAS Student Education Committee. Today's webinar will be moderated by Valentina Stampi-Bombelli of ETH Zurich in Switzerland. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you are not already. Our dues are minimal, only about $20 per year, to support the publication of our flagship journal, Adsorption, contribute to travel grants and workshops, seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at @adsos for future updates regarding IAS events, webinars, and information about scientific meetings. Please help expand our YouTube channel by subscribing. We would like to remind the viewers of the upcoming Fundamentals of Adsorption Conference in Broomfield, Colorado, between May 22nd and May 27th in 2022. More information can be found on the website given on the slide. The presentations given in today's webinar and for the webinar in August are by the recipients of the Best Poster Award in the inaugural IAS Twitter Poster Conference, which was held between the 7th and 11th of December 2020. The 5 recipients were chosen by a committee of judges, most of which were members of the IAS Education Committee. All 5 recipients were invited and have agreed to give talks in the July and August webinars. So now I'll hand it off to Valentina to introduce our first speaker today.
Thank you, Nick, and hello, everyone. I hope you can hear me well. So our first speaker today is Danny Shade. Danny Shade is a PhD student in chemical and biomolecular engineering at the Georgia Institute of Technology. He expects to graduate in the spring of 2022, so in less than a year. Danny completed his bachelor's degree in chemical and biomolecular engineering at Johns Hopkins University in the United States in 2017. And currently he is doing an internship at the Dow Chemical Company in the reaction engineering group. His research interests include gas adsorption for separations, tunable nanomaterials for adsorption and catalysis, and process modeling for adsorptive separations. During the webinar, you can send your questions via the Q&A tab on the Zoom if you are in the Zoom, or if you're watching via YouTube, you can also send the comments there, and us Zoom panelists will read the comments from there as well. So Danny Shade, please, the floor is yours, and good luck for your presentation.
All right, thank you, Valentina. Like Valentina said, I'm a student at the Georgia Tech. I'm working on my PhD in chemical engineering. And today I'm going to talk to you a little bit about adsorption of gas mixtures in metal organic frameworks. So I'll just give a quick outline to start. I'm going to talk a little bit about what adsorption separations are. I'm sure this audience is already pretty familiar with that, as well as ideal adsorbed solution theory and metal organic frameworks. I'll go into a little bit about the adsorbance we used in this work, some of the adsorption measurements and gases we used in this work, and then look at a little bit about how well the ideal adsorbed solution theory was able to match some of the experimental results that we saw. I'll start a little bit into some GCMC simulations that we very recently started running, looking to explain some of the results that we've seen. And then I'll finish up by talking about some of the other projects that I've worked on as a student at Georgia Tech. So as many of you probably know, adsorption is a process by which molecules basically adhere to an interface or a surface from a bulk phase. And selective adsorption of one or more components from a mixture can enable chemical separations. So some examples are shown to the right: water harvesting, medical oxygen concentration, and CO2 capture, are just some examples where adsorption separations can offer effective chemical separations. So looking at the ideal adsorbed solution theory, this is a thermodynamic theory to allow prediction of mixed gas adsorption from only pure component adsorption data. This method is very, very popular because mixed gas adsorption is difficult to measure, where pure component adsorption is much easier. However, this theory assumes some ideal behavior which is not always present in reality, and so these predictions are not always perfect. We're going to be looking at some metal organic frameworks today, and so I'll just quickly introduce this class of materials for those of you who have not seen them before. These are tunable high surface area materials made up of metal nodes connected by organic ligands to form porous structures. So I show this classic figure of Moff 5 here, as well as some of the aluminum Moffs that we made in some previous work. And these materials are nice because we can tune them either by introducing pendant functional groups into the pore space, or maybe by changing the identity of the metal nodes. So plenty of opportunity for customization, which makes these materials very attractive for research and separations. The Moffs that we're going to be using in this work are two UIO66 Moffs. One which is just a parent Moff or an unfunctionalized Moff, and another which includes a pendant amine group, which will be introduced into the pore space. So by introducing this functional group, we can introduce a little bit of different pore chemistry here, which might make adsorption properties different, especially for polar or quadrupolar molecules. Our third Moff we're going to be looking at is the copper Moff HCUS1, which incorporates something called an open metal site, or a coordinatively unsaturated metal center, where the copper metal atoms can be open to interact with adsorbates. So these are three fairly well-studied Moffs, and we chose these to represent some tunable aspects of Moffs. And so when I say tunable, what I mean is basically these Moffs are examples of using pore chemistry or open metal sites to basically change adsorption properties. So looking at some of the basic characterization of these materials, we can see from the powder patterns, we did indeed synthesize the Moffs that we set out to make. We can look at the nitrogen physisorption data and see that our surface areas and pore volumes are comparable with what has been previously reported. So looking at the gases that we're going to use in this work, we chose gases likely to give both ideal and non-ideal behavior because we were interested in looking at which factors can cause non-ideal behavior. So we chose molecules of different sizes, different polarizabilities. Here I have the kinetic diameter plotted. You could also look at molar volume as a measure of size, and in this case, you might find that the molar volume of butane might be substantially larger than some of these other molecules. But what we ended up going with was N-butane, ethane, methane, and carbon dioxide. So we chose these hoping that mixtures of alkanes might give us relatively ideal behavior, whereas mixtures of an alkane with CO2 might give us less ideal behavior. So the first step in any good adsorption project is to measure some adsorption isotherms. And so what we've done here is basically measured pure component isotherms at 298 K for each of the three Moffs that we have, and for butane, ethane, and carbon dioxide going left to right. We can see that HCUS1 has the highest uptake of all the gases at pretty much all pressures. This is because at low pressure, this Moff has the highest surface area, so there's a lot of surface area for gas to stick to at low pressure. And then at high pressure, where we're starting to fill up the pores in the Moff, this Moff HCUS1 has the highest pore volume. And so this is, as we expect, this Moff generally has higher uptake of most gases than the others. we do see that the amine functionalization gives a small increase to the CO2 capacity of the UIO66-NH2 Moff. This has been reported before, and so this is in line with what we expect to see. So by measuring pure component isotherms at different temperatures and using the Clausius-Clapeyron equation, we can calculate the isosteric heat of adsorption for each of these components. So we can see that there is some substantial uncertainty here, and this is largely due to the sharpness of the isotherms that we measured for N-butane, and somewhat for the other components as well. So I'll start on the right here with the plot for carbon dioxide heat of adsorption. So here, especially with this blue curve for HCUST1, we can see that we start at a relatively high heat of adsorption, and as we start to absorb more gas, this heat of adsorption starts to decrease. And so what this indicates is that at low coverage, we start to fill sites that are very favorable to absorb CO2. And then as we start to fill those very favorable sites, the CO2 starts filling in on sites which are less energetically favored for adsorption. And so this is indicative of something called energetic heterogeneity of the adsorbent surface, basically meaning there's a distribution of different adsorbent sites on the surface of the adsorbent. And so these different adsorption sites will offer different energies for CO2. So for butane, we almost see the opposite effect. So we see a bit of a decrease here as we start filling in some of those more favored sites, but then we see a pretty sharp increase in heat of adsorption with loading. And so rather than being a surface effect, this is actually the effect of butane molecules interacting with each other as the pore space starts to fill. So here we kind of get the opposite effect where we are starting to increase our heat of adsorption with loading. And in the meantime, or I should say in the middle of the slide for ethane, we don't really see either of these effects being very pronounced. Instead, we see a heat of adsorption that is relatively constant with loading. So we can hypothesize by looking at some of these adsorbents and some of these mixtures that some of these will display more ideal adsorption behavior than others. And so, like I said, we chose these adsorbents and these mixtures hoping to see a spectrum of ideal and non-ideal behavior. So again, if we look at an open metal site Moff, this might be a very non-ideal adsorbent. A Moff with a pendant functional group might be a somewhat non-ideal adsorbent, and an unfunctionalized Moff might represent the most ideal adsorbent that we're looking at in this work. And like I said earlier, for the mixtures, we can see that mixtures of alkanes and CO2 might be expected to be less ideal than a mixture of two alkanes. So to test how well we match up with the ideal adsorbed solution theory predictions, we had to measure some gas mixture adsorption. So the mixture adsorption results I'll talk about today were measured by my colleague Lucas on a breakthrough adsorption instrument. And so this kind of instrument is basically an open flow method to measure adsorption of either pure gases or mixtures. And so by flowing in a mixture of gases with mass flow controllers through a packed bed, we can basically monitor the outlet concentration of each gas using a mass spec. And we'll get plots like the two shown at the bottom center here, where we can see, how much time it takes each gas to flow through the bed. And so if a gas takes a longer time to flow through the bed, we can assume that that's because it's being sequestered by adsorption in the adsorbent that's packed into the bed. And if the gas comes out very quickly, we can assume that it's not adsorbing. And so by integrating the flow rate at the outlet of the gas over time and subtracting from the inlet flow rate of the gas, we can basically find the amount of gas that has been absorbed. So what's really nice about measurements like this is that we can control the equilibrium pressure and gas composition. And so this allows us to basically pick points in kind of the two-dimensional space of pressure and composition so that we can make easy comparisons and make good visuals. So first I'll show some of the mixture adsorption results for our UIO66 Moff. So these were done at a temperature of 298 Kelvin and a total pressure of 0.667 bar. So immediately, if we start on the left, we can look at our ethane carbon dioxide mixture, and we can see that our loading of ethane in the green triangles is much, much lower than what the ideal adsorbed solution theory predicts. And so already off the bat, for our relatively ideal adsorbent UIO66, we're already seeing some pretty large deviations from what IAST predicts here. So if we look at kind of the plot in the center, we see that actually IAST is much better at matching the predictions for adsorption of butane and carbon dioxide mixtures. So already we're seeing something we don't expect, which is that our greater size difference for butane and carbon dioxide is giving us somewhat more ideal results than our ethane and carbon dioxide mixture. And if we move to butane and ethane, we again see that the ideal adsorption solution theory predictions are relatively good, certainly better than for the mixture of ethane and carbon dioxide. So looking at this, I think we can certainly say that there is substantial negative deviation from IST prediction in the loading of ethane when mixed with carbon dioxide. And so if we look at the next slide here where we have the amine functionalized UiO66, we can see basically the same experiments run for this material. And again, we have pretty large negative deviations for loading of ethane in a mixture with ethane and carbon dioxide. Here, we also see that the loadings are fairly well predicted for the weaker adsorbed component in mixtures with butane. Here we also see that the butane is slightly higher than what IAST predicts for our butane adsorption. And so this could be due to butane adsorbing on the interior surfaces of the system, or perhaps that there's some variation sample to sample between what we use for our pure component measurements and our IAST and our mixture adsorption measurements. So moving to the open metal site Moff HCUS1, here we expected that this might be the most non-ideal surface with a lot of energetic heterogeneity due to those open metal sites. And so here we again see some negative deviations for loading of ethane in our carbon dioxide mixtures. That's very consistent across all three Moffs we looked at. But again, we see relatively better predictions for loading of butane and carbon dioxide mixture. However, now we're starting to see some positive deviations from ideal adsorption solution theory. And so when I say positive deviation, I mean that our experimental loading is going to be a little bit higher than what our IAST prediction says. So this is a little bit more unusual than a negative deviation. And so here we see also this effect for loading of butane and ethane mixtures. So it's possible that this could be due to some size difference of the two molecules. When we look at butane and either carbon dioxide or ethane as a co-adsorbate, butane is substantially bigger. However, this is N-butane, so it's larger, but it's sort of flexible and maybe could worm its way into smaller pores. But what we have here could be consistent with loading of the smaller molecules in the small pores of HCUS1, whereas the butane maybe doesn't access those pores as effectively. So after looking at these three mixtures, we decided to check a fourth mixture rather, a mixture of carbon dioxide and methane. So here I plot from left to right the three different Moffs we've talked about, UiO66, amine functionalized UiO66, and HCUS1. And so here, whereas previously we saw negative deviation in the loading of ethane when mixed with CO2, now our loading of our alkane is fairly well predicted by IAST, but our loading of CO2 is not. And so here we're again seeing those negative deviations in the loading for our more strongly adsorbed component. And this is true across all three Moffs with this exception of this positive deviation here in loading of CO2 on amine functionalized UiO66. So we had predicted that, looking at some of these adsorbents and some of these mixtures, that we might be able to, say without actually doing any experiments, which ones might be more likely to behave in an ideal manner and which ones might be less likely to. And so if we kind of plot how ideal we think the adsorbent is and how ideal we think the mixture is, we hope to see more ideal behavior for a more ideal adsorbent and a more ideal mixture. And so, I think this is a fairly straightforward hypothesis. But if we look at sort of what the reality is, we see that it's very difficult to predict when adsorption behavior is not ideal. And so some of you in the audience might be asking, I didn't know there was a way to quantify how ideal adsorption behavior is with a color. And so I'll just quickly mention that the color scale here is basically determined by the product of the error in IAST predictions of total loading and selectivity. So this is very much not a quantitative description of how ideal this adsorption behavior is, but this is just meant to kind of give a general sense of how in line with IAST predictions each system tends to be when we do the experiment and measure what the reality is. So as we seek to explain some of these ideal adsorption solution theory deviations, my colleague Brandon has very recently started running some GCMC simulations, and today I'll talk about some of the preliminary results that we have for the framework HCUS1 with a mixture of ethane and carbon dioxide. So here again we see some negative deviations between our experiment and our GCMC prediction. So again, our predictive method is giving us a higher loading of ethane than we actually see in our experiment, whereas our prediction for adsorption of carbon dioxide is relatively accurate. And we can look a little bit into why this might be. So one of the things that we can do with these GCMC simulations is turn on or off electrostatic interactions. So when we do this, we can see that the GCMC predictions for adsorption of ethane and carbon dioxide on HCUST1 are strongly impacted by electrostatic effects. So specifically, if we look at the adsorption of CO2 in the presence of electrostatics, we have relatively high adsorption. And if we turn off those electrostatic interactions, we have much, much lower adsorption of CO2. I think this is probably as we expect, since the quadrupole of CO2 will interact electrostatically with parts of the framework. But if we look at ethane, we can see that there's very, very little difference in the presence or absence of electrostatic interactions. And so what I think this illustrates is that our energetic heterogeneity for adsorption of CO2 is in part due to electrostatic interactions. And I think many in the audience will attribute these to the interaction of carbon dioxide with an open metal site in the HCUST1 framework. So looking at some of the conclusions here, we basically see it's very difficult to predict when IAST will agree with experiments. We saw many negative deviations from IAST, which are consistent with energetically heterogeneous surfaces. And we also saw that the GCMC simulations, which we're working on now, might help us to explain specifically which types of interactions are important in dictating the surface heterogeneity of the different MOFs. Right, so with that, I will talk a little bit about some of the other projects that I've worked on in graduate school. So the first project that I had the pleasure of working on with my colleague Bart was this synthesis and adsorption in aluminum MOFs. So this project was inspired by difficulty replicating a synthesis in the literature and looking for ways to synthesize a MOF using a different procedure. So we were able to synthesize several aluminum MOFs using basically a unified synthesis procedure. And so one of these MOFs, the CAU10 MOF, we were interested in placing different functional groups into the pore space to investigate the effects of pore chemistry, and not only pore chemistry, but also geometry of functional groups in the pores on adsorption properties. And so if we think about the UIO66 MOF that we talked about, there's a terephthalic acid ligand with a functional group on it. And so in our case, we chose an amine functional group. And if we look at the terephthalic acid ligand, there are basically four geometrically equivalent positions to add a functional group. In this isophthalic acid ligand in CAU10, there are two different positions. So here we can add, say, a nitro group sticking directly into the pore space, or we can add a nitro group that sticks more towards the side of the pore space. And so when doing this with nitro functionalized MOF and with a MOF with a pyridine ligand, we basically saw huge effects on the adsorption properties of the MOFs depending on where in the pore our functional group was. So another project that I've recently wrapped up is working on the Mcgas, which some of you may have heard of. If not, Mcgas stands for Multi-Component Gas Adsorption System. My colleagues Will, Bart, and Harvey helped me out with this project. And so here we have a schematic of this instrument that we designed, automated, and validated for gas mixture adsorption measurement. And on the right, I just show some of the validation measurements looking at mixture adsorption of methane and ethane on BPL carbon. So a project that I did last summer when our labs at Georgia Tech were shut down due to COVID-19 was working on this Bison 20 database, which I think has the potential to be very, very useful to the adsorption community, and in particular, the mixture adsorption community. So this database that we constructed, led by my colleague Xu Qing, is essentially the largest collection that we're aware of mixed gas adsorption measurements. And so we screened over 10,000 papers by hand. We identified over 200 papers with binary mixture experimental data. We characterized some of the adsorbants that were available, the mixtures that were covered in this data, and then we also looked a little bit at the reproducibility and some selectivity and IAST efficacy for certain adsorbants. So I think this project in particular is likely to be very useful to the community, because I think we've probably all read papers where we see the introduction, and in the introduction, a very common idea is that there is a scarcity of mixed gas adsorption data. And I certainly don't want to argue with that point, but I do want to say that maybe there is a little bit more of this data out there than we might have previously thought, and now it is all in one place. So in doing this search for screening of mixture adsorption data, I, as an experimentalist who has built a system for mixture adsorption, I was really intrigued by just how many experimental methods are out there for measurement of mixed gas adsorption. So, this is a problem that's classically considered to be very difficult. It's a difficult type of experiment to do. And so it makes sense that the creative folks in the adsorption community have attacked this problem in a number of different ways. So this review paper aims to collect all of the experimental methods used in the open literature to measure adsorption of gas mixtures. And so we were able to identify at least 18 distinct experimental methods. We talk a little bit about which of these will be likely to be in greatest use in the future, which ones might make sense for your research group to start using if you're interested in measuring mixture adsorption, with certain constraints. And here I have to thank my colleague Brandon again for his help putting this work together. So finally, I'll talk about a quick project using Moff adsorbance as catalysts. And I know this is not a catalysis audience, so I will focus mostly on the Moff aspect of this project. But so one of the materials that we talked about in the main talk today was this UIO66 Moff. And so we can actually also use this UIO66 Moff as a heterogeneous catalyst for biomass upgrading. So here my colleague Nima and I were able to basically synthesize some defective UIO66 using a trifluoroacetic acid modulator. We were able to kind of change the pore volume by heating them off up to very high temperatures. And then using different pore chemistries, we were able to kind of optimize the catalytic performance of this Moff to run the Garcia-Gonzalez reaction. Okay, so with that, I will move on to my acknowledgements. I'd first like to thank my collaborators, Lucas, Bart, Will, Brandon, Shuqing, Yi, Nima, and Farhad. These guys all have been very, very helpful to me, both in learning and in getting some interesting work out into the community. I'd of course like to thank my advisors, Krista Walton and David Scholl, whose mentorship has been very helpful. And with that, I would also like to thank my entire research group. This is the Walton group, who I spend most of my time working with at Georgia Tech. They've been great to enjoy time with and to bounce ideas off of over the past 4 years. So finally, I would like to acknowledge my funding and partners, which are the Department of Energy, which funds my project through RAPID, and our industrial project partners on that project are also shown here. So with that, I would like to welcome questions and comments and add that if you'd like to contact me after the talk, you can reach me at the following email address or my LinkedIn page. So with that, I will be happy to entertain any questions. Thank you.
Thank you very much, Danny. And I'd like to say thank you also on behalf of the whole adsorption community that you and your colleagues took the time to screen all of these papers to determine all of the multi-component gas absorption. So thank you very much.
Yeah.
We are
Absolutely.
getting some questions. We already have a question from Zoom and a few on YouTube. So we have a first question from Celio Cavalcante on Zoom from Brazil. And Celio said, nice talk, Danny. Could you give us a preliminary on how the GCMC simulations shall help the IAS modeling predictions?
Sure. So I'll just go back to that slide quickly. And so one of the things that we're interested in here is looking specifically at electrostatic interactions with different materials. So a classic way that we examine heterogeneity of an adsorbent surface is to measure heat of adsorption and look at variations in heat of adsorption with adsorbent loading. But here we're interested in looking at kind of the impact of electrostatic interactions, primarily in this HCUS1 framework, but I think also in the other frameworks as we start to think about maybe UIO66 that might incorporate some defects in the structure. And so we anticipate that this will give us insight into kind of what causes the energetic heterogeneity of the adsorbent surface. And we hope that this might give us a little bit more insight as to whether we can predict before making mixed gas adsorption measurements, how a surface will behave ideally or non-ideally. So thank you for that question. Thanks,
Danny. We have a question from YouTube by Adrian Hannenbauer. Telling great talk. Did you analyze the defectivity of the UIO66 frameworks? This Moff is known to have different number of defects depending on the synthesis, which can influence the adsorption.
That's great. So that's a great question, and that's something that we have not done yet. So kudos to that question. I think that's a great point. And like I talked about in our catalysis project, UIO 66 is, of course, known to have defect sites open. So we can have missing ligand defects, missing cluster defects, and so these can affect greatly the pore volume of the material. They can also start to break down some of the assumptions that we might make in our GCMC simulations, where we're looking at kind of a regular unit cell. And so it's a good point that UIO 66 does contain defects. Certainly, I don't think our samples are perfectly defect-free, although they're probably not as defective as the samples we were using in the catalysis project. So this is a great point. This is something that is worth looking into in the future. Thank you.
Thanks, Danny. We actually have a question also from Nick Wilkins, asking, have you considered using RAST explicit models such as the dual site Langmuir model to see if they are able to predict competitive adsorption? If so, how well do they match the experimental data that you have?
Yeah, that's a great question, Nick. Thank you. So looking at kind of the deviations that we're talking about in this project, it's sort of, we can approach this from a framework of looking at deviations that arise from interactions of adsorbents with the adsorbent, interactions of adsorbates with the adsorbent surface, or interactions between adsorbed molecules. And so when we talk about real adsorbed solution theory, we're interested in looking at interactions between adsorbed molecules. And so, Nick, I think this is a great question. We have not looked at other sort of thermodynamic theories like RAST or even HIAST for looking at some of those adsorbent-adsorbate interactions. This is certainly something that would be interesting to look at in the future, and I certainly hope that we have time to do that.
Thanks, Danny. We have another question from YouTube from Caroline Foe. Hi, Danny. How reliable are the heat of adsorption measurements for N-butane, given that you're calculating these values with the Clausius-Klapeyron equation and the isotherms for N-butane are so sharp?
That's a great question. Thank you, Caroline. So when we look at these heat of adsorption measurements, these are actually calculated by measuring adsorption isotherms at different temperatures. So here we're measuring adsorption. I'm showing adsorption at 298 K, but for this Clausius-Klapeyron method of calculating heat of adsorption, we're also measuring heat of adsorption at 288 and 308 K. So by looking at the differences in loading at different temperatures, we can basically calculate what this heat of adsorption looks like. And so this is challenging when our isotherms are very, very sharp. And so looking at these isotherms, we can see, especially for butane, there's a huge quick increase in loading at very low partial pressures. And so, a number of experimental errors might happen at these low loadings. There are challenges both with associated both with measuring low loadings, but also with measuring low pressures. And so, the sharpness of this isotherm does give rise to some challenges in calculating the heat of adsorption. So thank you for that question.
Great, thank you, Danny. I suggest we move on with Nagesh's presentation. So if anybody else has any questions for Danny, please continue writing them in the Zoom chat, in the Zoom Q&A or on YouTube, and we might have some time later on as well. So thank you so much, Danny, and talk to you later. Thank you.
Okay. All right, thank you, Valentina. I'll go ahead and stop sharing.
Thank you both, Danny and Nagesh, for your presentations. We also thank all of the attendees for joining this webinar. And we hope that it was both educational and enjoyable. An edited version of this webinar will be posted to the IAS YouTube channel with an announcement on the IAS Twitter feed. The hope is that the work discussed today will be a useful resource for the adsorption science community in the future. Our next IAS webinar will be on August 17th, also at 10 a.m. EST, with the remaining Best Poster Award winners of the inaugural Twitter Poster Conference. The one following that in September will be given by Hideki Tanaka, and we will update you of the date when we have one. Announcements regarding the upcoming webinars and other IAS online events will be posted to our Twitter feed and will be emailed to you through the IAS mailing list. We hope that you will join us.